Jupiter has been photographed by human instruments for well over a century. Its swirling storms, its great red spot, its shifting bands of colored cloud, all of it has been studied, cataloged, and photographed extensively by ground-based telescopes, by the Voyager probes, by the Galileo and Juno spacecraft, and by the Hubble Space Telescope for decades. So when NASA pointed the James Webb Space Telescope at Jupiter's North Pole on Christmas Day and published the results, most people reasonably assumed there wasn't much left to genuinely surprise the scientists studying this planet. That assumption turned out to be wrong. Because buried inside that new data is a specific, carefully measured, peer-reviewed physical puzzle that the lead researcher on the project has openly admitted his team does not currently understand. A combination of brightness recorded simultaneously by two different telescopes that, according to the physics they know, shouldn't be possible to produce at all. This is the real story of what NASA's James Webb Space Telescope actually revealed at Jupiter's poles, and why one of the world's leading experts on planetary auroras is still, in his own words, scratching his head. I'm your host, and this is your channel. If you want the real science behind the biggest mysteries coming out of deep space, subscribe now, because we're just getting started. To understand why this particular discovery caught the scientific community so genuinely off guard, it helps to understand exactly why Jupiter's magnetosphere has remained such a persistently fascinating subject for planetary scientists, decades after our first close-up observations of the planet. Jupiter possesses, by a wide margin, the strongest planetary magnetic field anywhere in our solar system, generated deep within its interior and extending outward to form an enormous protective bubble around the entire planet, one so large that if you could somehow see it directly from Earth, it would appear several times wider than the full moon in our sky. That magnetic field traps and accelerates charged particles, and it interacts constantly with an unusual built-in source of additional charged material that no other planet in our solar system has quite like it. Io, Jupiter's innermost large moon, one of the most volcanically active bodies ever discovered, constantly ejecting sulfur and other charged particles into the surrounding space environment, feeding directly into Jupiter's already ferociously energetic magnetosphere. The combination of that extreme magnetic field and Io's constant particle contribution produces auroras at Jupiter's poles that dwarf anything Earth ever experiences, both in physical scale and in raw energy output. Jupiter's auroras are hundreds of times more energetic than Earth's own northern and southern lights, and the glowing regions surrounding its poles are large enough to comfortably swallow our entire planet. Scientists have spent years studying this system using a combination of tools, ground-based observatories, NASA's Juno spacecraft conducting direct measurements from orbit since 2016, and the Hubble Space Telescope's long-running ultraviolet observations of the same polar regions, gradually piecing together an increasingly detailed picture of how this extraordinary magnetic environment actually behaves. What the James Webb Space Telescope added to that ongoing body of research was a specific technical capability no previous instrument had reliably provided: genuine sensitivity to rapid moment-to-moment change in Jupiter's auroral activity. On December 25, 2023, a research team led by Jonathan Nichols of the University of Leicester used Webb's near-infrared camera to observe Jupiter's northern auroral region at a wavelength of 36 microns, specifically chosen to detect emission from a molecule called trihydrogen cation, or H3A+, produced when high-energy electrons collide with molecular hydrogen high in Jupiter's atmosphere. Because this particular molecule emits strongly in infrared light, Webb's instruments were exceptionally well positioned to track its behavior in far greater temporal detail than any earlier observatory had managed. The team's working expectation, based on their prevailing scientific understanding at the time, was that Jupiter's auroral features would shift and fade gradually, evolving over a timescale of roughly 15 minutes or so, consistent with how researchers generally believe these large-scale magnetospheric processes unfolded. What Webb's camera actually captured instead genuinely surprised the team. Nichols described the moment vividly, calling the observation quite a Christmas present, one that, in his own words, blew him away. Rather than the slow, gradual variation everyone anticipated, the team observed the entire auroral region fizzing and popping with light, in places changing meaningfully by the second, a level of rapid variability that had never been documented this clearly before. The specific H3+ emission the team was tracking turned out to be far more variable than previously believed, a genuine and immediately useful finding on its own, helping researchers refine their understanding of exactly how Jupiter's upper atmosphere heats and cools over time. But the truly strange part of this story emerges when you look at what happened when researchers combined Webb's infrared data with a second, completely independent observation taken at the exact same moment. Because while Webb was watching Jupiter's aurora in infrared light, NASA's Hubble Space Telescope was simultaneously observing that same auroral region in ultraviolet wavelengths, giving the research team a rare opportunity to directly compare how the identical physical event appeared across two very different parts of the electromagnetic spectrum, captured at precisely the same time. That comparison produced a result Nichols has openly described as bizarre. The brightest emission Webb detected in infrared had, according to Nichols, no real counterpart at all in the corresponding Hubble images taken in ultraviolet light during that same observation window. This wasn't a subtle mismatch explainable by routine differences in instrument calibration or sensitivity. According to the physics governing how these emissions are produced, generating the specific combination of brightness recorded simultaneously by both telescopes would require an unusually large quantity of extremely low energy particles striking Jupiter's atmosphere at once, a scenario that, prior to this observation, scientists had generally considered essentially impossible under the conditions believed to exist within Jupiter's magnetosphere. Nichols was refreshingly candid about where this leaves the research team's current understanding, stating directly that this discrepancy has left them scratching their heads, and that they genuinely do not yet understand how this particular combination of brightness could actually occur. It's worth taking a moment to appreciate exactly what kind of statement that is and why it matters. This is not vague, hedged language crafted for a press release. It's a specific, directed mission published in the peer-reviewed journal Nature Communications that a carefully measured, dual-instrument observation has produced a real physical result that doesn't currently fit within the established scientific models, describing how Jupiter's magnetosphere and atmosphere are supposed to interact. Somewhere in the relationship between Jupiter's overwhelming magnetic field, the constant particle contribution from volcanic Io, and whatever process is actually generating this specific combination of infrared and ultraviolet emission, there's a physical mechanism at work that current planetary science simply hasn't identified yet. Nichols and his research team have laid out a clear, honest path forward, rather than claiming to have already solved this puzzle. They intend to continue investigating the specific discrepancy between the Hubble and Webb datasets, working toward a fuller understanding of what it might mean for the broader physics governing Jupiter's atmosphere and surrounding space environment. The team also plans additional follow-up observations using Webb, this time intending to directly compare that new data against measurements collected by NASA's Juno spacecraft, which has been conducting close-range, direct measurements of Jupiter's magnetosphere since 2016 in hopes of finally identifying the actual physical cause behind this still unexplained bright emission. It's worth situating this specific discovery within the much broader context of everything Webb has continued to reveal about Jupiter since becoming operational. This Christmas Day observation wasn't an isolated curiosity. It's part of an ongoing, sustained research effort using Webb's exceptional infrared sensitivity to study Jupiter's atmosphere and magnetosphere with a level of temporal precision that simply wasn't available to scientists before. This telescope existed, work that complements decades of prior observation from ground-based telescopes, from NASA's Juno orbiter, and from Hubble's own long history of studying these same polar regions in ultraviolet light. What makes this particular discovery genuinely worth your attention isn't just that it produced another beautiful image of Jupiter's aurora, striking as Webb's imagery of this planet consistently is. It's that a carefully planned, technically sophisticated scientific observation, using two of the most advanced space telescopes ever built, working in careful coordination, produced a specific, reproducible physical result that doesn't currently fit inside the framework researchers have spent decades constructing to explain how the largest planet in our solar system actually behaves. That's not manufactured suspense built around an exaggerated headline. That's the honest, on-the-record acknowledgement of the lead scientist himself, published in a peer-reviewed journal, describing a real, unresolved question about a planet most people assume we already fully understand. So here is where this genuinely stands right now. A century plus of observing Jupiter, and a telescope specifically built to peer toward the very edge of the observable universe, still managed to find something at the pole of our own solar system's largest planet that its own research team didn't fully anticipate and still can't completely explain. Auroral activity flickering and shifting by the second, far faster than anyone had previously documented with this level of clarity, and a genuine, unresolved physical puzzle hiding inside a routine Christmas Day observation, involving exactly how much low-energy particle activity would be required to produce the specific combination of brightness two of humanity's most powerful telescopes recorded at the exact same moment. Researchers are actively working to answer that question right now, planning further Webb observations and direct comparisons against data from Juno. Until they succeed, Jupiter, a planet most of us assume is already fully mapped and understood, remains host to a genuine, unsolved mystery playing out in plain sight at its own magnetic poles. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists measured and said, rather than exaggeration, hit subscribe and turn on notifications. because there's a lot more of our own solar system left for this telescope to reveal. Drop a comment telling me what you think is actually causing that unexplained brightness at Jupiter's poles, and share this with someone who still thinks the planet Jupiter has no real mysteries left to solve.